Hello everyone and welcome. Let's now understand why at this point we are still not taking advantage of on-push change detection and everything is getting re-rendered. Remember, on-push change detection works by comparing inputs by strict equalities. So if we pass in here a new list of messages, we are going to re-render the whole thing. Now, the list of messages that is getting out of the store is not changing each time, so we are only changing the reference to that list if there is a change inside the list. But the problem is that that is being applied, so that logic of keeping references to unmodified data as much as possible, that logic is being applied to the application state coming out of the store, but that's not what is being passed on to the view. Let's switch back to our application, to the thread section component for example, or let's switch back to the message section component. So as we can see, the data that is coming out of the store is immutable and keeps references to previous data as much as possible. But what we are passing in to the view is, for example, the values of the messages observable. That, as we can see, are message view models. This is not the application state. This is the result of taking the application state and applying this selector function, which is essentially a mapping function that returns the exact same results each time. So that is the problem. Our selector function is the problem because it's creating a new object each time. It's creating a new array of messages each time and it's passing it to the view. So from the point of view of the view, even though the data inside the store is immutable and reuses references as much as possible, from the point of view of the view, we are always receiving a new message view model array. So we need to apply some similar logic to what we did inside the store. We need to apply it to the selectors. Let's see how we can do that. Let's take one specific example, the messages selector. We can see that the message selector is taking the application state and it's returning a list of message view models. So the way that it's doing this is it's going to the current thread. So what we have here is the ID of the current thread, and what we have here is the current thread that is currently selected. We are going to take the list of message IDs of the currently selected thread. Then, based on this list of IDs, what we are going to do using the current list of message IDs of the currently selected thread is we are going to obtain an array of messages. So let's have a look at the type of this variable. As you can see, it's of type message array. So this is the list of message objects that we have from the store. And the way that we have built our reducer functions, if a message did not change, we are going to receive a reference to the exact same message object. And in our particular application, the message never changes, right? We don't edit the message. We only receive new messages on the current thread, for example. Now here we are taking the messages one by one and we are applying a mapping function that we have defined here. So if we are passing in the same message, we are going to receive exactly the same message view model. So let's quickly switch back to the view. What we really want to do here is whenever, let's say, Alice sends a message to Bob, hello Bob, what we want to do here in this re-rendering is we don't want to re-render the whole list, right? We only want to add a new message at the end. But all of this data that is already here, and the thread could be long, all of these DOM elements that are here, they are unmodified. So we really don't want to regenerate the whole HTML, the whole DOM tree for the whole message section list. We really only want to add one DOM element to the end which corresponds to the last message. So what we want to do here is point to the previous messages because they were not changed and simply add one new message at the end. So this function here, we are going to modify it to perform an optimization where the following will happen. The first time that we pass in a message to this mapping function, the mapping is going to be applied, but the result of that mapping is going to be kept for further reference. Now, the second time around, if we receive the exact same message object, and we know that it's immutable because it's coming out of the store and everything is frozen, if we receive again the same message exactly, then we already know what the result of the mapping would be, and we have kept it in memory for further use. So the second time around, we are going to return the exact same mapping result. So this property that we're going to about to add to this mapping operation is called, in functional programming terms, memoization. Memoization is an optimization that we can apply to a pure function that doesn't have side effects, meaning that for the same exact inputs, it will always return the same exact output. So if the function has that property, if the function is said to be pure, we can perform the following optimization. For a given combination of inputs of the function, we produce the result the first time, and we keep it in a cache local to the function. The next time around that the same function is called with the exact same inputs, instead of calculating again the result, we are going to return the result that we already have from the cache. So let's see how this new functional programming concept, memoization, will actually solve our problem and enable us to leverage on-push change detection effectively. This is coming right up in the next lesson.